Okay.
This is Google Chrome.
Which page?
Oh, very good. Let's go. My topic is quantum memory Rubidium-Raman scheme. And what is a quantum memory? It is a device that stores and retrieves quantum state of light, such as single photons, while preserving their quantum properties such as phase, coherence, and entanglement. Its application can be for quantum repeater for long distance, long optic fiber, and then quantum memory would delay the quantum channel and wait the classical channel. So what is a good quantum memory? Its requirement is high storage efficiency, long coherence in storage time, and then high fidelity state preserve, and on-demand readout, compatibility with telecom wavelength. And then hardware implementation of quantum memory for mainly one atomic vapor, which is this Raman memory, and then called atomic ensemble MOT, rare earth dot crystal, which is a solid state, and MV sensor in diamond.
What is MOT?
I don't know.
Electro-optical trap. Electro-optical trap. Usually combination of magnetic field and laser. You look for this is very robust setup. Very important setup. Maybe it would be good if the student can come and do PhD or build this up.
And then this is the parameters. For warm vapor, it's suitable in room temperature, in storage time within micro to millisecond, and it can have wider bandwidth and low complexity. Bandwidth means we can have a different bandwidth of laser. And core atom is in ultra cold temperature, in a millisecond to 100 millisecond. Bandwidth medium, complexity high. Rare earth crystal is in cryogenic, means very cold, and then its storage time is millisecond to minute, quite long, but bandwidth is very low, and capacity high. And MV center is in room temperature or low temperature, and storage time millisecond to second, bandwidth low, capacity high. So which one is better? And here is for fast quantum communication, a warm vapor Raman is better. And long-term memory, long-term storage is rare earth crystal. And scalability is cold atoms or solid state hybrid because it can fit in a IC.
Give some numbers on the memory card, order of magnitude.
This one.
Bandwidth for the cryogenic temperature or vacuum temperature. Order of magnitude.
Why Rubidium-Raman quantum memory is popular is because it works at room temperature, avoid excited state of incoherence, high bandwidth in simple 3-level scheme, compatible with single photons. This is an example rubidium Raman scheme setup. The first one is they arrange it in a Zeeman magnetic color state. And this is the rubidium cell. The gas inside here, and then got a shading. This is a description for the figure. First, it make it in ensemble. And 3-level structure, detuning, and 2 ground state. I will describe later. The first method is to create a frequency gradient. 2 specially warm magnetic coils surrounding the cell were used to produce opposing linearly varying Z1 shift along the cell. Switching current between these coils created a switchable atomic frequency gradient in our storage medium. The cell and coils are surrounded with emitter to reduce the influence of the Earth's magnetic field.
Check what is emitter. Is it new metal? New metal. New metal. You check.
The temperature of this is in 78 degrees Celsius, and the number of atoms is 4 times 10 to the power of 12 atoms. And what is ensemble? It is not one atom, it is many atoms acting together. Means in this cell we got many atoms. And then a single photon is absorbed collectively. Means by the whole atom, all atom. And state change is in one of the atom where we don't know which.
Right. Mathematically, what do you mean by this state? Single atom excited by absorption of one photon. Just one equation is the state. Later I'll show you.
This is the 3-level system. The atomic 3-level structure is the G1 is ground state and G2 storage ground state. E is excited state. We mostly want to avoid it because we don't want to excite it and emit the spontaneous emission. The 2 ground state exists due to the hyperfine splitting, which means this 1 and 2 is also a ground state, but in the ground state we split into 2 different frequencies. And this is what rubidium looks like.
Five of these, the nucleus is not stated.
Yeah. This left middle one is 85 and the right side is the 87. The 85, the bandwidth between the 2 hypersplitting is 3 point something gigahertz, and then 87 is 6.8 gigahertz. So 87 have a larger difference between the frequency, so we use the 87. Within
I can identify D1 line and D2 line. This one is D1 line and D2 line. And then also the wavelength. This one is giving the 782 nanometer. How come? How come we have 778 two times? Should be one time only. We need two photon absorption. It goes. We need the blue laser. No. You check, huh?
This is not Google.
Oh, it's let me see. Oh, it goes to the D level. Okay, D level. Then how about the typical one? We go to the 780.
This one.
The P. Yeah. Two photon absorption. How about the right one? The right one, how is the transition? Also go to the same D. So we did it separately, right? So S and D.
Within each isotope, the actual ground state 5s half is not a single energy level, but is within a two hyperfine level due to interaction between the electron spin and the nucleus. The rubidium 87 hyperfine is F1 and F2 given by 6.8 GHz. We need to initialize the system by using optical pump. First, to make sure all is at the same state, which means it's at G1, not G2 or someone in G1. And then we need to shine a laser at frequency at G2 to E. And then from the E, we will drop back to either G1 or G2. But if it drops to G2, it will get excited again and drop to G1. Then it is settled by using this optical pump. And then what is detuning? Detuning is the laser frequency minus atomic transition frequency. In Raman memory, both lasers are far tuned from the E, which means its original excited level, excited state. And the purpose is to avoid real excitation, suppress spontaneous emission, and preserve coherence. Atomic state is in superposition. An atom or ensemble is described by a quantum state, as this one, for example. And then the C, the magnitude of the C square is the population, and the single C is the probability amplitude. And the phrase of C carries quantum information. We do know at which state, but there is a probability in which state. So this is superposition. And here is the example of the state. For example, in this state 0, the first one is represent the state 0. So we put 1 in this matrix. So for 1, and for the state 1, it can this place represent the 1, so we put 1 in here, this place. This state is a matrix. And this means the probability amplitude is 1, the state 1. This means the probability amplitude is 1 and state 0. And then we times this is the probability amplitude. And we times with the state. And this gives the matrix alpha, beta, like this, which it times into this alpha and then add it up. And then the alpha square is the probability of the state. It is in state 0. And then for beta square, it is the probability in state 1. So they both add up to be 1. And what if we have more than 2 states? We just add another one below the matrix, so it can represent a 3 state. This is the example of the if the amplitude is by this line, and then we can get in the y-axis, but the probability is the area under the graph. So this is example of it.
What is sine? What is phi?
I just take this picture and explain the probability, amplitude, and the probability. In density matrix, we want to see the coherence. So the coherence is the off diagonal, which means not this one and this one, because this is diagonal, and off diagonal is this and this. So if it is 0, then means coherence is lost. And this is the density matrix. This is the state just now, and this is the inverted, which means this is cat and this is bra. And bra is the transpose plus conjugate, which means this matrix we transpose and then add a conjugate. So this whole density matrix will be looks like this, and then simplify to this. And inside the alpha, we got the magnitude and its phase. So in beta also, and this is if beta is conjugate, then we minus its phase, because conjugate means its phase is become negative. So when in pure superposition, which means incoherence, this diagonal is not 0. When this alpha is this number and beta is this number, you can work it up to become like this. And in case 2, if phase is high, it's still coherent because it goes up, it is odd number, a -1, not 0. In case 3, it is decoherent, which means the phase is random and its average out will be having a 0, so it is not coherent.
Incoherent. We need to write incoherent. The word should be incoherent.
Or not decoherent. Not decoherent. I put a to represent not.
A proper word is the without the off diagonal, the system is considered incoherent. But the coherence is the karma is the loss of coherence. The coherence and incoherence is different. And it's different.
So non-incoherent is incoherence. This zero.
You can say after a long time the coherence, which is the off diagonal element, will go to zero because of decoherence. Decoherence is a process. It's a process that causes the loss of coherence.
So, two-photon Raman transition is signal photon frequency, which means single photon is from G1 to the excited state plus detuning. And then control laser is a continuous beam. Its frequency is from G2 to excited state plus detuning.
You write the frequency is omega. Omega G1 equals to 1 minus omega E equals to 6. When you're mixing up the state and the detuning is not a state. And you do the control of frequency.
This is a formula for the effective Rabi frequency. This is the speed of transition. And this shows that as you increase detuning to avoid noise, you must increase laser power omega control to keep the memory fast and efficient. A spin wave generation is when this transition happens across billions of atoms in a Weber cell. It creates a collective spin wave, a pattern of atomic excitations that physically encodes the phase and amplitude of the original signal photon. So this is the right process. First, the control laser is on, and then this red one, and then the atom do not actually jump to the excited state. Instead, they undergo a two-photon Raman transition through a virtual level. This process maps the quantum state of the photon onto a collective spin wave, a synchronized flipping of atomic spins across the entire region ensemble. And after the single photon is go in, it will go to the G2, and the control laser is off immediately to avoid it goes back to G1. Then after some time, where we need to we turn on the control laser, And this pulse interact with the spin wave to trigger simulated Raman scattering. The atomic excitation is converted back into a photon that carries the same quantum properties, which means phase and polarization as the original input. This is the formula for effective Raman coupling rate. So like this. And this efficiency formula for it, and optical net and retrieval efficiency. Also a phase matching and a control determining trade-off, which means we want to avoid excitation, we need to increase the control power. And then this optical pulse schedule. Dynamic rules for write and read, writing process and read out process is given by this formula. And also the period of the rubidium, which will cause it incoherence faster or not.
So the T tau is the coherence time. Is it the coherence time of the spin wave? And eta is the coherence. Eta is the coherence, right? Is the off diagonal element. Is it? What is eta?
I think this is the formula for the rubidium decay. I think it is off diagonal.
We check. I think it's off diagonal. We check the same. And then the tau is it called the coherence rate? Or storage time? Which one? I think we try to define the definition for tau and eta.
Advantages of the Raman scheme is have higher bandwidth. Unlike other methods like EIT, Raman memory can store very short broadband pulses, nanosecond scale, because it operates off resonance, and high fidelity. Recent 2025 to this year, research has demonstrated Raman memories in rubidium with efficiencies exceeding 82% and conditional fidelities up to 98%, making them viable for quantum repeaters. And worm vapor compatibility, rubidium Raman memories can function effectively in room temperature vapor cells, avoiding the need for complex cryogenic cooling. Thank you.
Very good.
Okay. Any question?